So, good afternoon, everyone. So, in the first part of my talk, I'll be discussing a little bit regarding the microstructure and phase development in cements. And I'll be continuing from the place where Professor Bishnoi stopped. There could be a little bit of an overlap. So, the first question is, what is a cement? So, cement is a hydraulic binder that hardens when you're mixing it with water. And these are typically fine powders having particle size range somewhere from 100 nanometers to 300 microns, and that hardens when mixed with water. Right? A brief history of cement. The first calcium silicate cements were produced by Greeks and Romans. So what they found out that if they are mixing volcanic ash with lime and water, you are able to produce a hardened mortar, and that acts as a very good binder for construction. So somewhere in the middle of the 18th century, John Smeaton, he was generally credited as one of the first civil engineer. What he discovered that certain impure lime, or lime is calcium oxide, certain kind of impure lime, when you're mixing it with water, has some latent hydraulic properties. And then the term Portland cement, that was first applied by Joseph Aspdin. His British patent number 5022 describes a process for making an artificial stone by mixing lime and clay in the form of a slurry and calcining the dry lumps of the material in a shaft kiln. Right? So what he did was he made this calcined material called as clinker, and he ground it to produce a cement. Of course, the name Portland cement comes from the fact that the hardened material or the stone which you are getting resembled a very commonly found stone. Or commonly found limestone, Portland stone in Dorset, and that is how the name Portland cement comes in. But of course, there are other claims to the discovery as well, like Professor Shashank was mentioning in talk that in France, there was Louis Vica who claimed that they were the first inventor of this Portland cement system, right? So it's very interesting when you're looking. So the Portland cement was first discovered in Leeds, in UK. So when we are looking through some of the images, historic images, artwork produced at that time. So this is a painting by a famous painter known as Thomas Kilby. It's called as A Day in Wakefield. What we see is that if you can see a very small kiln here. So when he was drawing the landscape, he has actually caught the vertical shaft kiln, what Joseph Aspdin was using to make his cement. So it's very nice to see the history, or it has been actually captured in this artwork. And this is a pub in UK where we try to go, but you can see it is kind of now in a very bad shape. So this is supposed to be the last surviving building, which is made of the original Portland cement, which was manufactured by Joseph Aspdin. And if you're more interested to learn a little bit more about the history of how Portland cement came into be, I would suggest you to read a very nice article by Professor Ian J. Richardson, where he discusses all the different aspects of how Aspdin cement has varied from the modern day cements. So with this, I would also want to give a brief introduction. What is concrete? Because sometimes there is a bit of a confusion. So if you take some cement and you just mix it with water, it becomes a cement paste. So if you take some cement, water and sand, it becomes mortar. And if you're adding some coarse aggregate into mortar, it becomes a concrete. And the advantage of concrete is that it is a very versatile material. You can produce it at a very low scale. You can see it's a localized mixing, or you can also produce it in a highly controlled manner in RMC plants, right? So cement hydration, again, Professor Shashank kind of hinted on this, or he was discussing a lot on this as well. So there are 4 major phases in Portland cement with A-lite and B-lite, which are tricalcium silicate and dicalcium silicate respectively, being the major phases present in cement. So typically in an Indian Portland cement, you would expect somewhere between 40 to 50% of A-lite, somewhere between 15 to 25% of B-lite, right? Of course, the composition, it is going to vary depending on the type of raw material you are using to produce the clinker, depending on the different factories. But this is the typical range which we have found, like 40 to 50% A-lite is typically very common for Indian cements. So what happens when it reacts with water? Again, I am using the cement chemistry notations here. So C3S, tricalcium silicate, it will react with water to form CSH gel, and CSH gel I have not put any composition because it is a material which does not have any fixed composition, right? And produces CH. CH is calcium hydroxide or Portlandite. Similar reaction with C2S as well. C2S is dicalcium silicate. When it reacts with water, it forms CSH and CH as well. The other important consideration is that the CSH gel, that is the main hydration product or the main binder of your Portland cement reaction, accounts for approximately 50 to 60% of the volume of the solids present in a hydrated cement system. So the structure, it's a very poorly crystalline material or a semi-amorphous gel, right? So gel like, it's a material which has a gel-like property, and its role in the hydrated cement system is the fact that it is a primary binding phase, and it is mainly responsible for giving strength to the cement system, and it has a foil-like morphology at a nanoscale. Right? Calcium hydroxide or Portlandite or the good hydration product, approximately it accounts for 20 to 25% of the solids. It has a very large, distinct, large hexagonal platey-like structure. So if it is allowed to grow freely, it will form a very nice hexagonal crystal structure. So it also plays an important role. It acts as an alkaline buffer. It helps to maintain the pH of concrete approximately 12.5, and this plays an important role in passivating or preventing the corrosion of rebars. Right? Of course, there are other reactions in cement as well. You have aluminate reaction. So you have aluminate, that is C3A, that is tricalcium aluminate. So if it directly reacts with water, it forms something called as hydrogarnate. Now we don't want this reaction to happen, because once this reaction happens, your cement reaction is kind of poisoned. It does not react further, right? So in order to prevent that, what we do is we add gypsum into the cement. So when the gypsum is present, the C3A or the calcium aluminate can form needle-like ettringite. Now this ettringite is known as an AFT phase. It has a very distinct needle-like shape. And if there is still C3A remaining, what could happen is the C3A can further react with ettringite to form these other AFM phase known as monosulfate, calcium monosulfoaluminate or monosulfate. So this C3AH6 or the direct reaction of this aluminate phase with water is one of the reasons behind the flash setting of cement. And we are adding gypsum to prevent the flash set. So the degree of clinker hydration, there are many techniques to measure how much of clinker is reacting at a particular age. So one of the most commonly used technique is X-ray diffraction, about which I'll be talking in the next section. What you can see here is that typically after 24 hours, approximately 55 to 60% of your clinker is reacting. And this degree of hydration goes up to nearly 85% after 90 days. So this is a typical, the red line is an OPC hydration, the clinker reaction in OPC. And you can see that it is a very nice continuous curve with an approximate reaction of 50% at 24 hours. That increases up to around 85% after 90 days. Of course, this kind of a clinker hydration behavior is not similar in the case of blended cement system. For example, you see these lines which are kind of flatlining. So these are the systems with calcined clay in them. So what we observe is that if you're adding calcined clay to the system, a lot of the clinker hydration is kind of leveling off after a certain point. Of course, you can see that the early age, first after 24 hours, the degree of hydration is very high because of the filler effect of supplementary cementitious materials in the blended cements, like Professor Piyush was mentioning in the previous discussion. So why is the clinker hydration flatlining? So if you look individually at the degree of reaction of A light and B light, what you see is that your A light is continuing to react mostly okay, even in the presence of calcined clay. But what happens is that the reaction of your B light is kind of completely flatlining in the presence of your calcined clay. Right? So this is a very interesting challenge. We are still trying to figure out why this is happening exactly. But typically, if you're having high B lightic content in your clinker, and you are using that to make blended cements with aluminate-rich SCMs, you could expect that your overall clinker hydration is going to slow down a little bit. Right? So the phase assemblage can be of the hydrating cement system at different ages can be easily studied using an XRD analysis, you can see the phase development at 1 day, 7 days, 28 days, and 90 days. You can see a strong portlandite peak after 1 day, which is due to the fact that your C3S and C2S is reacting and producing a calcium hydroxide. But as the days increase in the blended cement systems, you can see these are with calcined clay, OPK, you can see that your portlandite content has completely reduced by 90 days. There is no more portlandite which is observable. But in the case of cements with limestone, or in the case of OPC with quartz, you see a strong portlandite peak. Of course, this is expected. Why? Because there is no supplementary cementitious, or there is no pozzolanic supplementary cementitious material in these systems. Additionally, we can also see the formation of these AFT and AFM phases. So one of the key reaction mechanisms of blended cement like LC3 is the fact that your ettringite is stabilized, and you can see that in OPC blended cement system, you are able to find strong ettringite peaks even after 90 days, whereas in other systems, there is a slow transformation of this ettringite to monosulfate, right? And the microstructure development, it is also important. So why does the cement gain strength? What happens is, as the hydration reaction proceeds, more and more hydration product forms, and it starts to fill the voids. For example, you can see a scanning electron microscopy image of this is of an anhydrous cement. You can see all these black spaces, these dark black spots. These are the porosity of your system. Because the hydration has not started, there is no hydration product. But after 180 days, you can see those kind of black spots are completely reduced. You can see that the microstructure is very dense. You can see a lot of hydration products. Of course, there is some porosity, but the porosity has significantly reduced because your hydration products such as CSH, ettringite, etc. Am I not audible? Okay. So what happens is these hydration products are filling the volume, and it is minimizing the porosity. And this porosity and strength has a very strong relationship. So there is a fundamental relationship that the higher the porosity, lower is going to be your strength, right? And so what happens in cementitious system is that, that the porosity is getting minimized by the formation of these hydration products. So you can see that this fundamental relationship exists for many materials such as zirconia, for iron, for plaster of Paris, sintered alumina, etc. So higher the porosity, lower is going to be your compressive strength. So our objective is to minimize the porosity in the system, and this is exactly why blended cements such as LC3 work, because due to the pozzolanic reaction, a lot of hydration products, additional CSH gel, carboaluminates, ettringite, etc. are forming a very densified microstructure, and that is going to minimize the porosity, and it is going to refine the porosity. It is going to improve the strength as well as the durability performance of these blended cements. So what Power suggested was that he suggested something called as a gel space ratio. What he said that the strength of the cement can be expressed as a function of the gel space ratio. So gel is the volume of all the hydration products which is forming in the system. So if you are able to divide the volume of the gel with the sum of the volume of gel and the capillary porosity in the system, you are able to get a very nice relationship, a cubic relationship. Of course, this Power's gel space ratio model, what we see is that these parameters 2, 34, and 3 are not going to be very fixed. It's not going to be fixed. Depending on the systems which you are studying, it might vary. But this exponential or relationship between gel space ratio and the strength is fundamental, and it does exist. However, it's a very simplistic approach, I would say, especially if you have effect of something known as interfacial transition zone. If you have some motor, microcrack, etc., this relationship might not hold true. But still, a gel space ratio gives us a very good idea to link the hydration product formation and the microstructure formation and the strength development, right? So we have understood that the porosity in the cements is going to be very critical when you're trying to analyze the strength development. So in cement, there are several types of pores. So it could be what is known as gel pores. These are the interparticle spacing between the CSH gel. It could be capillary porosity. It could be some entrained air bubble. So what we can try to do is, in case of certain if you want to ensure durability in certain extreme condition. For example, if you are casting your concrete in a location where it is expected to have significant freeze thaw damage, there are certain admixtures which you can use to entrain some air bubbles. So this air bubbles will help to relieve the pressure. You could also have these entrapped air voids in your concrete. So what entrapped air void is, because when you are not compacting your concrete properly, it could have some entrapped air voids also present. What is important is that typically it is going to be your capillary porosity onwards that is going to affect the strength development. So the gel pores, so these are the pores which are very much intrinsic to the CSH gel. So these are the pores which are present in the microstructure of the CSH gel. Typically the porosity or the size is going to be varying between 0.5 to 2.5 nanometers. So as we saw before, CSH gel is a very colloidal amorphous, has a colloidal amorphous structure, and it is having these pores approximately a few nanometers in size. So this is the sheet-like colloidal kind of structure, and you can see the porosity here. Now these porosities are going to be filled with water, and these are known as the gel pores. And you can see here, so this is the unhydrated cement grain. You can see these gray hydration products circling the unhydrated cement grain, and then this becomes the gel porosity is inherent in these CSH hydration products. Now you could also have this gel pores, which is approximately around, so if you look at CSH gel, it has a porosity of approximately 28%. But it is important to keep in mind that these sizes, it is small to have an adverse impact. So these pores are of smaller sizes. It is not going to significantly affect the strength and permeability of your cement systems. Right? Now capillary pores are the spaces in the hydrated cement system which are not filled with solid components of the hydrated cement paste. So you can see here you have the unhydrated cement grain, you have your CSH gel which contains the gel pores, and you see these dark black circles. Now these are the capillary pores, and capillary pores have an impact on your strength development. The pore sizes are going to range somewhere between 10 nanometers to 10 micrometers. So voids larger than 50 nanometers, they are going to be typically having a significant influence on determining the strength and the permeability characteristics. If your voids are smaller than 50 nanometers, it is referred to as micropores, and these are going to play a significant role in the volume changes, that is in drying, shrinkage and creep of your concrete, right? And as the hydration proceeds, because your microstructure is getting filled with hydration products, it is getting refined, you can see an overall reduction in the cumulative porosity. And this reduction in porosity is very important because first, the reduction in porosity implies that there is an improvement in the strength. It is also going to minimize or reduce the permeability of the concrete, and that indirectly will be improving the durability performance. That is, it is going to make it difficult for these deleterious ions such as sulfates or chlorides to move from the external environment into the concrete because of the lower porosity, right? The other point or another important point in the microstructure of cement is something known as an interfacial transition zone. So this interfacial transition zone is the weakest link of the microstructure. So typically approximately 15 to 10 microns. So if this is your aggregate, approximately 15 to 50 micron distance from your aggregate surface, it is known as an ITZ. So it is caused by, or it is a zone of higher porosity within the hydrated microstructure. So typically why it forms, it is because of something known as wall effect, because near the aggregate size, near the surface of the aggregate, the cement particles cannot pack very efficiently. So typically you will observe that this section will be having a higher porosity compared to the rest of the bulk cement paste, bulk cement mortar. And typically what you see is your calcium hydroxide tend to precipitate along this region. The reason is why this ITZ forms is because of the fact that particles cannot pack very efficiently near the surface of the aggregate. So the characteristics, it's high porosity compared to the bulk paste of the system, less CSH, mostly it is going to be filled with calcium hydroxide crystals, and there is going to be a high localized water cement ratio near the surface of the aggregate because of the inefficient packing of the cement particles in the ITZ. So why is it important? Because when you are applying a load, the cracking pattern happens along the interfacial transition zone due to its higher porosity. You can see that this is a magnified microstructure. The crack pattern is forming along the surface of the aggregate, or along the weaker part, or along the line where there is higher porosity, right? So what can we do? So you can see this is an OPC. This is a microstructure of an OPC and an LC3 system. LC3, like I said, is a blended cement with calcium clay and limestone. You can see that the surface from the the approximately 15 microns from the surface of the aggregate, you have a section of high porosity. The high porosity is very clearly visible with respect to the black pores. You can see very clear porosity here. You can see a lot of calcium hydroxide being precipitated in the ITZ. Whereas if you have a blended cement system like LC3, you can see that this place, the porosity has significantly reduced. You don't see any calcium hydroxide in the ITZ. Why? Because all this calcium hydroxide is getting consumed by the reaction of calcium clay as a part of its pozzolanic synergetic reaction in LC3 system. So again, if you are having a normal strength concrete, again the failure is expected to be along the base. But if you are able to strengthen the ITZ to a certain extent in high strength concrete, you will see that the failure, depending upon the strength of your aggregate, it is going to be mostly through the if you're able to the aggregate. And this is a realistic, the real image. So you can see there are two types of failure. You can see an interface failure where the failure has happened through ITZ. And you could also see the aggregate failure, because when you're applying a load, it is going to break the aggregates instead of the base because you have strengthened the ITZ, right? So to summarize, we have talked quickly about microstructure development. We have talked a little bit about phase assemblage and porosity and strength development in hydrated cement system.